So hi. No, I'm very seriously, before we get into the recording part, I would like to point out that I am not a member of the core team. I am a FreeBSD committer, and that these comments have nothing to do with the FreeBSD Foundation. And with that out of hand, let's talk about security and what it means to the BSDs. And I would like to include all of the BSDs in this. I will point out that this is our current record for all BSDs for security. This is a job accident sign from a construction site. Anyone who looks at, all right, I'm going to have to pace. Anyone who looks at security on computers and security of operating systems and security of large systems knows that basically something breaks every day. Not on OpenBSD or NetBSD or FreeBSD, but in computer security, every day is a new disaster. Right? So we have hardware disasters like Spectre and all these other things, which now we can't even trust the hardware. We have software disasters. Those come from various problems, and I'm going to try and talk about those at a higher level. Right? So I'm not going to talk about a lot of specific technologies, but I want to talk about our approach as a group of systems people who are supposed to understand security and secure systems and think about how we can do a better job and how, in particular, the BSDs, all of the BSDs, can remain relevant in this area, right? So, you know, a lot of the security issues are not related to BSD, and to any particular BSD, but there are approaches and things that we can do, get out of my way, to make, hopefully, things better. Because, personally, I would like the world not to end because some idiot created an IoT device that kills all of us. Because that is what's very likely to happen. So let's talk about three approaches or three ways of thinking about security. And this is, I call this the optimistic fantasy, right? So, you know, you read a lot of books about computer security and security generally. You read Schneier, you read Anderson, you read all these people, and you read about what they say, and you look at all the protocols. And, you know, people like to think about security in the same way that people in the, I don't know, 14th century thought about security. And so you have defense in depth, and we have walls, and we have a gate, and we have a moat. I'm sure there are alligators in this moat. And, you know, we believe that if we build a system that has enough defense in depth, that that system is secure. Often, the optimistic fantasy includes this concept that security can be finished. Now, I'm pretty sure that people in this room don't believe that, but I'd like to disabuse you of the idea. So, you know, this is kind of this optimistic fantasy of where we are with security, that we're building things that matter and that we're building the right defenses in the right place. But the problem is that this fantasy doesn't work because what we're building isn't solid, right? We're building on software, and software is nearly infinitely malleable, subject to Turing. So you can build something like this, and then you have the pessimistic fantasy. So the other side of the security coin are the security people who have this idea that everything is on fire, or, you know, this is, I forget which castle this is. It's a castle in Britain that actually burned down. That nothing can be fixed, that nothing is ever going to work, that everything is always broken. And between those two fantasies are sort of the reality of what we actually have to do, right? So in the pessimistic fantasy, you know, this is where, oh, it's gotten dark. Well, the fire looks much better now. You can really see the flames, which is important. So between the pessimists, who believe that everything is on fire and that nothing's going to work, and the optimists who believe that they've built these great walls and this great moat, is the place where we all have to spend all of our days working. And, you know, as we spend time trying to make these systems work, we have to think about whether the pessimists are right, whether the optimists are right, and when they are right. One of the things that I'd like to talk about a lot more in this particular talk is the concept of time, right? So security, you know, people always call it an arms race. You know, one side does one thing, then one side does the other. But security is actually, building secure systems is a process. And as systems change, those processes change, and how we build those things has to change. So there is one more fantasy that I like to talk about. That's the paranoid fantasy. And yes, this is a specific dig. For those who don't know where that picture is, you can ask me later, but I'm sure people in the audience do know. The idea is that in the paranoid fantasy, it's not that everything's on fire or that everything's fine. It's that we can control what's going on by hiding things in a bunker, right? And while it's very interesting to be able to work on things in isolation, in the world of computer security, what matters is those machines being exposed to the outside world. So it's great if you have a very clever idea that's hidden in a basement, but if that idea is not actually tested and fielded and worked with the rest of the things in the world, it's not very useful. And the paranoid fantasy works very well for very, very niche types of systems. So the NSA used to run, maybe they still do, but at one point they only ran version 6 Unix, which was great because they only needed to do things that version 6 Unix could do. And they had read all the source code because it, wasn't that long. And so theoretically they could understand where all the bugs were, and that was very good. The thing was very tractable for them, but that meant that they weren't able to do things that we could do with more powerful computers. And that kind of paranoia works very well only in a niche. For the people who consume our software, the people we wish to consume our software, all of the BSDs, that software has to be usable and available to people who are not locked in a basement and don't have to get past guards with guns. So that's our 3 fantasies. And that's kind of where I want to start from the standpoint of what we have to think about. So the reality for all of us in this room and for all of us who work on large-scale systems and distributed systems in particular, and at this point, if your system isn't distributed, you're not participating in 90% of the world's systems because basically that's the world. The internet is the world, right? So our systems contain millions of lines of code, thousands of moving parts, and the biggest problem is that many security bugs are a surprise. They're not a surprise afterwards. Like you look at Heartbleed and everyone's like, oh, of course that's stupid, but nobody knew it was there, right? And the problem is that we're always surprised. And, average people don't really care, but those of us who actually work on this stuff would prefer it if these things weren't always a surprise. And part of that is because we have a scientific approach to a lot of engineering, but we often have a faith-based approach to security. We kind of hope that it works, right? We will test things internally, but we don't have the rigor that we need to make it so that we don't have as many surprises. So here's some reality thus far. I was trying to make some comparisons between some current operating systems. It turns out if you use the CVE database at MITRE, they specifically tell you not to do this. But my response to them is, well, to hell with you. I made this anyway. What I find really interesting is, and this is the kernel part of the code only, where's the laser? Kernel part of the code only. At this point, all of the major Unix-like and big operating systems have been around for about the same amount of time. I don't count Windows 3.1 because nobody counts Windows 3.1. But if you look at something like NT, which came from Cutler, coming from DEC to go to Microsoft, and then Linux, OpenBSD, NetBSD, FreeBSD, and these years are counted from a 1.0 release as reported by each operating system. Well, turns out Linux has a lot of CVEs, but it's also got a lot of use, right? And that's one of the things that's really important for us when we're thinking about security. One of the things that's really important is the only way to really battle test or field test software at this point is to use the largest test bed in the world, right? And the largest test bed in the world is the internet. So if your code isn't running on the internet, then who knows if it's secure? The other thing I find interesting is that NetBSD and FreeBSD have almost the exact same number of lines of code in sys, and yet different number of CVEs. I have question marks here because I was not able to find on either page sort of a list of users. I know that NetBSD, for instance, is used in routers in Japan and IIJ, so it's been widely deployed here. OpenBSD appears in some products, but I don't know all of them. Since I'm a FreeBSD person, I know where we are. And who knows how large the Windows NT kernel is. I'd like to not find out. But in terms of thinking about how you secure a large code base, all these code bases are about the same size, and they have about the same moving parts, right? So they all have file systems, they all have networking, they have all the things that people put in the 1980s, right? These have existed since, this shape of system has existed since I was in college and is relatively unchanged. POSIX, all of this stuff. So what's interesting to me is we've gotten to this point in history, they're all a quarter century old. They have varying numbers of CVEs reported against them, which is not really accurate. They're in a whole bunch of products. They're about the same size. How do we measure whether or not we've actually correctly secured them? Because the current measure of security is the front page of the New York Times, right? You all would like to think that that's not true, right? As technologists, we'd like to believe that we have a database of things that tell us whether or not something's secure. But for people who are not technologists, what they care about is the latest thing that happened to them or their data, whether their phone was broken into or their laptop or all their data disappeared from Equifax or some other place. But it's interesting to me that at this point in time, we can't really correctly quantify, is X more secure than Y? We can say that X fixes the bug Y that we found, but we can't say that we're better or worse because we don't have a good measure. And as people who do science and engineering, that's something that's really necessary, right? So right now, I can tell you whether or not something is faster or slower because I have a way to quantify that. But I cannot tell you whether or not something is quantifiably more or less secure. We can try to reason about it, but we don't have good measurements for us. And for people who consume our software, which are the people we're trying to supposedly protect, we don't have a good answer for them either. So, I put operating system in here, but this is true for any large system of code. This is the standard canon for security, right? So when someone comes to you and says, oh, well, we have to secure this thing, we're like, well, what are you securing against? What are the attacks? What are the countermeasures? And then there's this line that I'm going to keep harping on, which is, how do we measure efficacy? If in medicine, we measure efficacy as if I give someone a drug, does it make them better, right? If I give someone a particular technology, does it make them more secure? And the only way we ever find that out is when it's not, right? We don't have a positive measure of efficacy. We can say that we believe that there are certain programming paradigms and certain recommendations that make software more secure, but then we find out that the hardware has undone us, right? So at the moment, we don't have something we can talk about for efficacy. And I'd like to see us have that. So right now, when we talk about efficacy, we could talk about things like programmer testing. Like, what is the test coverage of 5 million lines of C code? Which I find really funny, by the way, because for those of you old enough in the audience to remember Ronald Reagan, unfortunately, I am that old, and Star Wars, not the movie, the technology. One of the arguments against Star Wars Defense Initiative, the idea that we were going to shoot down nuclear missiles with lasers, there are a lot of arguments for it. Like, it'd be really cool. Like, come on. Like, as a technologist, you're like, you want me to make a big X-ray laser and fire it into space? All right. That'll be $10 million. But one of the arguments against SDI, which I love, and you can go back and find this in the news, is that all of the computer science people who were asked about this at the time said, that's impossible. That's over 1 million lines of code. That'll never work. Well, all of our operating systems are 5 times that large, and I don't know if they work. And that's the real problem. We don't know if they work. So programmer testing, test suites, and then we have this thing of, okay, well, we know a bunch of attacks, right? We know a bunch of things that can be done to software, and we can try and test to see if those are possible with the mitigations that we've designed in the last however many years. But then, of course, the biggest problem is that the size of the unknown attacks is not actually even quantifiable, right? In software and in hardware, we can know the things we can do, but someone will always, well, thus far, someone has always come up with a bunch of attacks that people say, oh, I had no idea you could do that, or that's really clever. Well, that's really clever is very nice, but it's not very good for making sure that our systems remain secure. So we don't have this good measurement of efficacy. And that's one of the things I think we, as technologists, need to think about. So how do we do security that matters, right? So it's great, that all of us have our laptops and our whatever, and we're working on things, we're trying to make them secure, and we're trying to make them correct, because often correct is secure. Not always. But in terms of the larger scope of security for operating systems and for systems in general, how do we build things that matter? And I don't mean matter to the 100 people who are in this room, but I mean matter to the world. Because, again, I would really like the world not to end because some idiot made some terrible device. But I'm really, really convinced that's how it's going to end. So security that matters needs to be well designed, correctly implemented. We can argue about that for ages. Well-tested, field-tested, which I'm going to talk about a lot. Subjected to continuous refinement. And this last point is super important. And I'm not the first one to say it, but I'm going to come back to it again. When you discover that a mitigation doesn't work, it's time to get rid of it. When something has been shown to not be secure, it is past its sell-by date. We'll talk about sell-by dates in a moment. So how do we make security that matters? Well, well-designed. Know your history. So this keeps coming up repeatedly. We have seen over the last, 5 or at least 10 years of my career, people putting forth ideas that if they had just done a literature search would know were wrong, right? One of the really important things is that people need to at least know what other people have tried so that we don't reinvent the same broken wheel over and over again. And so history is really an important part of design. If you are working on something and you think you're working on, in particular, a security technology, and you think you've got a great idea, I'm sure it's a great idea, but really take 5 minutes. Like, Google makes this easy, right? It's not like you have to go to the card catalog in the library anymore like we did when we were kids. Community review. This is a thing of my thing against developing security in a basement. We all know that we hate design by committee. Actually, who likes design by committee, just in case? Okay, good. So we don't have to have anyone shot. But you should still be having someone else besides you review whatever it is. In fact, the one useful process for almost all sorts of technological design is the process designed by the IETF. RFCs are better or worse, depending on who's working on them, but a review process that includes real documentation of the design and running code is about the only thing that has proven in the last 40 years to be really effective. So having an RFC process, not with the whole world to start perhaps, but is a really important way to make sure that what you're designing and what you're building is novel and useful and hopefully doesn't have a lot of holes in it. And like I said, design in a basement is just as bad as design by committee. Correctly implemented. So this is one of the places where actually the BSDs have a lot of really good experience. If you compare the BSD, and I mean all of the BSDs, development processes to other systems, in particular Linux, you will find that the BSDs have a much more mature view of software development, whether that's the stability of kernel KPIs, the stability of APIs, release processes, release numbering, being able to understand what's running under you. The BSDs actually do this pretty well. One of the places that we've done better or worse as a community is review. So the various BSDs have various reviews of implementation. FreeBSD has this. I know the NetBSD and the OpenBSD folks have their own. reviews, but for many reasons, we don't have as much outside review as we might want. And by outside review, I mean, groups who are not both politically and emotionally invested in the code looking at what we're doing, because that's actually really important. Well tested. Anyone got a really amazing security test suite? Right, I didn't think so. There's definitely a need in open source to have security test suites. And the problem with this is, of course, security people by default are paranoid and not very good about sharing in a lot of ways. And so often when people develop attacks, they don't share them because, well, of course, if they share them, then everyone on the internet has them, et cetera. But there needs to be a solution to this problem. There needs to be a way to run a CI system on your software that validates not only the correctness of it and its conformance to whatever standard you pick, but also is able to test for the security things we at least know about, right? I mean, we're not going to be able to test for the unknown knowns. Known unknowns? Unknown unknowns? But this needs to exist. And we don't currently do a lot of direct liaison between the open source BSDs and the kind of people who would be able to do, for instance, a red team exercise or on your software. So these are sort of the things that a project could do that we'd like to see more of. But the other thing that really matters is this, which is field testing. So 5 hosts in a basement is not a field test. Field tests come from things like being integrated into products. Basically opening, putting the software out there so that it's being abused by up to 5 billion people on Earth. Because it turns out if everyone's connected to the internet and 10% of them are terrible people, that's a lot of testers. And that's what you want because it's the largest test bed that's ever been built. Also remaining involved in research. This is back to things like red teaming. I happen to be currently an American. We'll see if I am when I get back. So from my point of view, this is DARPA, but every large, national government has something like that. And being involved in security research with those people and making sure the BSDs are involved in those organizations, which for some people is politically distasteful, but for the rest of us, we realize that it's actually a really good place to get the kind of people who would be able to attack our software to tell us what they're doing. Sometimes they don't, but at least we'd like to have some of that. So field testing is actually incredibly important. There is plenty of really brilliant software that's been written by someone in their basement and has never been shared, and I don't care about any of that software. I care about the software that's going to run on people's devices, on medical devices, in hospitals, on airplanes. Those are the things I care about because that's what I'm going to interact with. I'm not going to interact with the brilliant piece of software that nobody ever shared. Continuous refinement. So, we do continuous integration on our projects. We really need security testing to be more automated. We need that kind of thing to be in a CI environment because that's the only way that we're going to make sure that we haven't screwed up. And then human review. Humans are annoying but necessary. Just telling you the truth. And lastly, software needs a sell-by date. And actually, this is not original to me. I think this is Paul Vixie who said this in a talk. But the moment he said it, I was like, oh my God, I just want to put this on a big billboard somewhere in Silicon Valley and smack people with it. For those of you who've never seen a milk sell-by date, you should not, sell by October 14th, because if you eat spoiled milk, you get really sick. And if you consume spoiled software, you also get really sick, but a different kind of sickness. So this is something we don't do very well in software generally. This is not a BSD-specific issue. People would like to believe that end-of-lifing a piece of software actually happens. As someone who just visited a factory in China where Windows 7 was used on all of the test fixtures, I can tell you that that doesn't happen. So being able to figure out a sell-by date for software and getting people to actually adhere to it, or disabling the software when it's no longer useful in a secure way, which is really hard, is going to be difficult. So software needs a sell-by date. Where am I? Right. I will pause here to refresh. Because if you think that Windows XP is dead, you're totally wrong. Next time you get an X-ray, ask the technician if you can look at the screen on the X-ray machine. And then run the other way.
Well, you might find
I might still run the other way. I know how you guys work. Well, honestly, I'd prefer an OpenBSD X-ray than a Windows X-ray. Because at least if I were poisoned, I could find one of you. So sell-by date's really important, and it's something that we don't do in any project, really. So let's talk about why we need sell-by dates. And let's talk about ASLR, because everybody likes to complain about how ASLR is brilliant or not, and FreeBSD didn't do it, and then we tried to do it, and then someone did it, and then things happened. But let's talk about what actually happened with ASLR, right? So address space randomization, also known as making it slightly more difficult for an attacker to attack your software, and making it really hard for you to debug it. So unsurprisingly, OpenBSD was the first to release this, but it then begins to show up in other places. Windows Vista, macOS. The macOS folks seem to put it into various things over the years. It doesn't really start to show up deeply embedded into kernels until this is like 11 years after OpenBSD shipped it. So you get Linux's KSLR, you get Android. FreeBSD starts integrating it in 2018. And then it turns out there's a problem with this. Here's the problem. Something called the ANC attack. It's one of the unknown unknowns. Now, the attack doesn't attack ASLR, the software. It uses a trick in the branch predictor of, well, you know, every modern processor that's ever been produced in the time that ASLR existed to get around ASLR. My favorite part of this attack is that it's not written in C. This attack can be written in JavaScript and shoved into a web browser. And there's this great video. Go find the video online. It takes about 5 minutes, where it de-ASLRs all of Firefox's memory in a few minutes, which doesn't mean that ASLR is bad. And it doesn't mean that ASLR was the wrong thing to do. What it means is any technology, ASLR or W cross X or all of these things, you need to apply them and you need to know how long they're going to be good for. Because at some point, someone's going to come up with a bigger bomb. That's how arms races work. Actually, in the US, we went for more accurate bombs. But whatever, there's bigger bombs. They destroy cities. It's bad. So since 2017, you can have ASLR, but it turns out there's some nice little JavaScript that'll get around it. So this is why you need sell-by dates. Now, we have a bunch of other problems. Here's a problem for this room. I love this because this is the argument we always have, right? It's C isn't safe, which we all know, and then we all try to get around it. We apply things, we apply tools, we run covariety, we run a bunch of static analyzers, we run a bunch of tests, and we're like, okay, well, we know it's not safe, but we're really doing our best until someone leaves a random strlen into a networking library. And then everyone's like, oh, that's fine, because there's all these new languages. We could write in Go, we could write in Java, we could write it in Haskell, we could write whatever. But it turns out all the alternatives to C are slower than C, at least as far as we can tell. Rust is now a little closer, but Rust is fairly new, and I still don't believe Rust is going to win. And so people propose all these alternatives, and then we're like, yeah, it turns out C is faster, and the world is made of C, right? Everything that matters in the world, airplanes, trains, phones, laptops, everything, every single processor in the world runs C. In fact, what it runs is assembly language, which is C without for loops. I mean, C is just assembly with for loops. Come on, seriously, and an if, and a nice if statement. I mean, it's a brilliant language, but it's not, that's all it is. So we wind up going through this loop over and over and over again, right? We don't have alternatives here. We'd like to have alternatives. People keep trying to turn them out. And the other problem is a market problem, right? So as technologists, I think often we'd like to, well, certainly we'd like to ignore marketing. My goal generally is to never talk to a marketing person. But the fact that we have put so much C into the world over the last 40-something years means that that is what the world is made of, and that's what we have to interface with. So even these new languages we come up with, like Rust and Go and whatever, pick your language of the week, they still have to interface to C, which is unsafe. So you're like, okay, well, now I've made this very small shim that's really safe on top of this stuff that is going to kill me, right? So it's one of the main cores of our problems, is that we need to figure out how we're going to limit C's ability, even though we need it, to shoot our foot off. I still have both feet. With apologies to the really good ACM talk that the Turing lecture you should find called On Trusting Trust. One of the issues in a lot of our systems is we don't have a good root of trust. In particular, this is one of the things that cell phones has improved on, but server technology generally does not have a good root of trust. This is slowly changing. And of course, as OS people, we tend to, well, trust the hardware might be a little strong. But often when dealing with hardware issues, we kind of throw up our hands. We're like, well, look, we have to trust the processor because we're running on it. And it's like, well, that's true. But it turns out over the last, 3 years now, almost all of the really interesting security attacks have been because of features in the processor. By the way, those features, like speculative execution, we asked for them. We, the operating system people, were like, we'll make the OS go faster if you give us this feature. Oh, yeah, I guess it's going to totally screw us in 10 years when we actually find out that it's not secure, but we'd really like it now. So, hardware is untrustworthy, but sometimes it's untrustworthy because we asked for that. And so many systems, depending on what you trust in the hardware, many systems lack a good root of trust. We'll talk about that in a minute. And I used to try and find images for this in code, but actually networking images are way better. Because it turns out if you just type in terrible network router to Google Images, you get a ton of these. Complexity kills. And let's talk about complexity a bit. One of the things that human beings are really, really poor at, and it turns out most human beings continue to be programmers. Programmers are humans, sort of, mostly. But humans are not very good at understanding complexity. And turns out operating systems are complex, and the systems that are built on them are even more complex. And in security, complexity is the enemy of security. When you are looking at building secure systems, one of the things that I really try to get people to do is pick the least complex option. Because it's not always true that the least complex is the best, but if you can understand, if you and several other people in the room can understand what it is, then you have a slightly better chance of not winding up trying to debug this in the middle of the night. All right. I need more drink. Although technically I'm not drinking. Okay. So how not to be helpful in security? Oh, yeah. Oh, I can just yell. Sorry. That's true. I don't know if this should be recorded. How not to be helpful. So this little graph was pointed out to me a couple weeks ago while I was working on this set of slides. This comes from our friends at Hardened BSD, which I have a different name for that I cannot put on the recording. And this is their easy feature comparison between what they think they've done and the rest of us. So you can see all these little check marks, and you can read over this feature comparison. And this was very interesting because, as someone who works on FreeBSD, my immediate reaction was, crap, did we miss something? I know that people have been whining about ASLR, and people have been working on ASLR, but there's a really long list here. And so then I went through the list, which took time, and I had to look up, oh, this thing, that thing. And what I found was that for the most part, half of these things are just compiler flags, which may not even work against some of the things in packages and ports. And the other things were not really important. So this kind of feature comparison, this is not helpful. Why is it not helpful? Because it's just FUD, right? This isn't really talking about what these things actually do. It's a bunch of check marks. And it's funny because when I brought this up and I was talking about ASLR, someone technical, not a marketing person, said to me, yeah, but it's just a checkbox. I'm like, if it's just a checkbox, why are we doing it? If it's not a protection, why are we doing it? We need to do actual protections. So this kind of comparison, not very helpful. Other things that aren't helpful. Secret little conversations on other networks. So security FUD, sells products, promotes projects, gets attention, which seems to be what really wants to be happening here. But it doesn't help move the state of the fart, state of the fart, wow. Paging Dr. Freud. Does not help move the state of the art forwards at all. This is not helping. This is not making the BSDs better. It's just, putting stuff on the internet. In fact, since a lot of this has been happening on Twitter, I think that like fake news, we should talk about fake OSs, but that's a whole other talk. So let's talk about security that matters. Since we're in Japan, I stole the Hokusai image, the tidal wave. I talked about how to build security that matters. Let's talk about where security is going to matter. Nobody cares about your laptop. I don't care if your laptop's secure. You know why? Because nobody buys them. And your laptop is probably not going to end the world. Although maybe, I don't know. I've seen Warner's laptop. Warner's laptop will probably end the world. But everybody else's laptop probably won't. These are sales figures. I apologize. This is about the real world as opposed to, other things. Go back. This is total shipments of laptops in third quarter of 2018. I couldn't find a good year, so multiply that out by 4. That's, 240 million laptops. Nobody cares, right? Because there just aren't that many. Smartphones, we used to care. It turns out smartphones have gone flat as well, but more people use them. In fact, most of the people introduced to the internet within 1,000 kilometers of where you're sitting have never used a laptop. They are using mobile phones, right? There's maybe where security mattered a bit more. And actually, it's a place where a bunch of people did some really good work on security because it turned out to matter. But where is this really going to matter? And I keep coming back to this. I've spent a long time doing embedded systems work. No MMU, none of these safety things that we take for granted in Unix. This is embedded. Now, of course, if you weren't technologists, I would use a different word, but we just talk about embedded systems. These little flat lines, these are enterprise shipments and consumer shipments. These are your laptops and servers, and these are mobile phones. And this is why security here matters, but security that only works here is not going to affect the world. And that's what we want to do. We want to have security that actually helps people who use our technology. Because our goal is, I think, generally our goal in this room is not to screw up so badly that we end the world. So you can't spell IoT, or you can't spell idiot without IoT. Why is that? So let's talk about what embedded is now called. Now people in this room are like, no, it's embedded systems. And I'm like, fine, that's great. But if I have to talk to a chief security officer, I'm not going to talk about embedded systems. I'm going to talk about IoT, because then they're going to pay attention. Here's the problem. All of the Unix-like OSs, all of them, every BSD and Linux, is not ready for IoT or pervasive embedded systems. People have taken the various BSDs and put them into embedded systems, generally put them up a light pole, and generally put them on private networks. The moment they went on public networks, they were totally rooted. Right? They were definitely insecure, and they definitely need a lot more work. This is aided and abetted by the fact that much of what the IETF did, while their design process was good as a design process for protocols, did not take into account a lot of security. Postel's advice needs to be reversed. Postel's original advice was be conservative in what you transmit and be liberal in what you receive. Right? That is incredibly great for designing a research network. That is appallingly bad for a network full of 5 billion humans, because humans are terrible. So BSD kernels and kernels generally are inherently trusting. We only have one real boundary, right? Kernel user space. Once something's in the kernel, game over, right? That kind of design, not really the right way to go for the world of idiot. And by the way, because part of this talk is to try and get this group of people to be interested in security that matters, it may not matter at all to us. Almost every embedded product that I come across, and I come across a lot of them, if it runs anything that's like an operating system, it's Linux. It is not BSD. It's not FreeBSD. It's not OpenBSD. It's not NetBSD. It's not hardened BSD. It's not Dragonfly BSD. No BSD. And what it usually is, if you want to talk about the things that are going to end the world, is someone, Bob, we'll call him Bob, some Bob at a university once made some version of Linux run on some embedded board that every factory in China is now going to put on an embedded board, completely unpatched. So if we want to talk about having the BSDs remain both secure and relevant, this is where we need to be thinking, not our laptops. So how do we remain relevant? Well, I've been pushing this paper at people now for about a year. This is given to me by Robert Watson, which if you want to talk about security, he really knows what he's talking about, thankfully. This is the iOS security guide. With a slide. The iOS security guide from Apple. Apple talks about everything from their hardware root of trust out through the applications to how things like FaceTime work, right? And you don't get the code because we're never going to get code out of Apple. You might as well give that up. But if you want to understand how someone thought in a mature process about securing a device that was going to be given to hundreds of millions of non-technologists, which is what the world is made up of, that is the guide, right? That's at least a starting point. We need to start adapting the OS, pick your BSD, I don't care who it is, to more to embedded environments. We run well on boards that are coming up to meet us, right? So thanks to Moore's Law, we get all the features we used to have in a DEC system or a VAX on an embedded board. But we need to actually be, as system software people, more flexible in how we're going to deal with embedded hardware, because that hardware is far more variable than server hardware. We need to leverage the hardware features that exist. We need to design systems for hardware security to fail, right? So there's, if I can trust the black box, what if I can't trust the black box? Right? Spectre is because we always trusted the black box. Or if we look at the DASLR, we trusted that box. So we need to both leverage the features that exist and know that we have to go around them. One of the things that would be amazing, and actually this is one of the places where the BSDs, in particular FreeBSD, can shine in embedded, is reliable updates. So how do you update your phone? Well, my phone's a phone. It's always on the damn network, right? So I can get updates to myself. But when you're thinking about embedded devices like a medical device or a power meter or any of these other things, using, for instance, boot environments, which Alan talked about yesterday, is one of the ways in which we can help move the state of the art forward in getting something like reliable updates. Because reliable updates are one of the ways to make sure that our software is up to date and that we can deal with the sell-by-date issue. Right? Because a lot of the things, like the TrendNet Micro camera, the reason those are still online is they can't be updated. Right? So you can look at everybody's house. Why would that be a problem? And then we've got a little unsolved problem here, which is secure kill switches. It would be really good if we could actually enforce the software sell-by-date. Right? The way Apple enforces the software sell-by-date is you just can't update your phone anymore, which works, but not the nicest way to handle that problem. And secure kill switches we need for things, all of the things that are infrastructure, right? All of the things that are infrastructure in the world are going to run some piece of software. And if we're not lucky, it's all going to run Linux. having secure kill switches is really useful. And finally, to end on an uplifting note, we need to work together better. So right now, each of the BSDs pursues its own path, which is fine. OpenBSD has a process they like, FreeBSD has a process they like, NetBSD has a process they like, etc. But to vendors, and this comes to the last line here, they don't care, right? They don't care that, you know, one group has a glorious leader and one group has an elected team. It doesn't matter to them. Like, we're all small potatoes. So from the standpoint of dealing with vendors from a security standpoint, the BSDs need to stand together, right? They need to coordinate and they need to work together in order to actually make things matter. So if you look at, I think it was the response to Heartbleed, which was, you know, among the various BSDs, was wildly uncoordinated, right? That is not good, right? That is bad for all of us. So having something like a BSD security working group, right, where people are actually thinking about this from the different standpoints, from open, from net, from free, et cetera, that I think makes a lot of sense. And that's something that if people are actually really willing to work on, I am willing to coordinate. Because otherwise, you know, we can hang together or we can all hang separately. And that brings me to the last slide, which I cheated and showed you. I didn't tell you which side of the fantasies I was on, but I'm pretty close to this. All right. Questions? Yes. Someone want to give that person a mic? It's an expensive mic. I don't want to run. Yeah, just her. Yes, she raised her hand. My God, I love this slide. Yes.
Okay. First of all, it's really like your suggestion that we should collaborate. You spend a portion of your lecture attacking an individual. That's not cool. And
Okay.
second, ASLR, it doesn't help in the context of a JavaScript, but it does help in other contexts.
Sorry, it doesn't help in the context of
JavaScript, because it does help in other contexts.
So, oh my God, I don't want to have to deal with JavaScript. But the JavaScript point isn't that it was just easy to implement in JavaScript. The JavaScript point is that it was easy to implement against the chip, right? And so, in terms of collaboration, and coming back to something like ASLR, the collaboration there would be more about knowing more about what the hardware can do to us. What I'm thinking about when I'm talking about collaboration is making sure that we present a united front when we actually find a security issue. So Heartbleed was a classic case of this, where the releases from all of the BSDs came out staggered at different times. There were issues with embargo, where if all of the BSDs were able to go to, say, Intel, and because I can tell you, I talked to Intel. Intel doesn't care, right? They really don't care about us. They barely care about Linux, but they really don't care about us. So the only way for us to get them to care is for it to not just be open or net or free or whoever, but to be a group of them. If you have a significant enough group, then you might be able to get them to care.
So what about the Linux distribution list?
What about it?
It's an embargoed list collaborating from all the Linux distribution and some of the BSDs.
And that is possibly another way to work, although I don't want to join it. I think the first thing to do is I think the best first step is for the BSDs to present a united front.
Yep.
Other questions? No, all the way down. We're going to make you run. Here, you can ask the question in the mic and then I can answer. No, it's okay.
I think part of the idiot wave will be the time T rollover in 2038, because when time is wrong, just think about the certificate expiries and all that. And given the lifespan of those devices, this should be really fixed all over the place early.
So I totally agree that time will break things, because that's something else I work on. And it's certainly one of the places we could look. See, in 2038, I will be retired. So any young person in the audience who wishes to work on the 2038 problem, I'll be living in a bunker by then. But yeah, that is the time to rollover is probably going to be a big problem for everyone. Other questions? It's really warm now. I think it's that. Yes, here I'll give him my mic.
You said that it's important to keep a front together with all the BSDs so that things like Intel, for example, will pay more attention to us. It will include us in the pre-disclosure and so on. But to be honest, I think Intel only cares about what people that buys Intel uses, basically. So in order for Intel to take us seriously, we need to have customers that uses our software and want to see our software fixed, because that's what they use.
Right, and I agree with that, and that's one of the places where at least the connections between FreeBSD and its downstream vendors is useful, because we can go to them and say, well, look, NetApp, Isilon, Juniper, blah, blah, blah. The other relationship that's probably really more important is ARM, right? And so, the FreeBSD project has a very good relationship with ARM at the moment. The problem with ARM is ARM doesn't produce anything, right? So it's ARM licenses stuff to other people. But yes, the best way to go about it is to have companies along with the community go and say, hey, we consume your chips in great volume and we really care. I'm going to make him run to you.
Please.
You talked a lot about security mitigations or checklists of security mitigations that you think don't matter. But what kind of security mitigations can I implement that do matter? Like, what sort of things can we do that you think are relevant and would make a difference?
So I think one of the things that would be great for there are two areas of security technology that I think, well, one in particular, which isn't a mitigation, but when I think about the security features I want to leverage right now that I can't on any of the BSDs are things like TPM, right? So we did some work with SGX on FreeBSD. SGX has a bunch of issues. Embedded chips now have more TPM because of this, right? Making it so that our systems are very easy to integrate and get things like root of trust out of hardware will go a long way for building secure systems. I do like, there's that laundry list. I do like a lot of the, make writable or XOR executable. I like that one because that's a very typical one. I think ASLR in 2003 was fine. I think the thing that I wanted to talk about in that arc was things don't remain fine. So certainly the executable page thing, TPMs. In the embedded space, the one that's really interesting is all of the root of trust that can be done for factories that we can get at that kind of stuff. And then, amusingly enough, getting random number generators right. And I don't mean the software ones. But if you look at laptop or server hardware, it's not a solved problem, but you get a lot more chip space to solve it. But if we're talking about the idiot problem, the IoT problem, if you look at what people produce to make the IoT devices, the amount of security hardware you get there is lower. And so looking at what you can get out of those, I think, is really interesting for us. Michael down here. He's right in the middle, so I'm going to make him run down.
One word. Blockchain. Discuss.
How does that even relate?
Enlighten us.
So you really like a data structure? Blockchain has nothing to do with security, right? And so I don't think it really relates to this. Blockchain is just a marketing term that I can use to get my article higher on the New York Times list. I don't think there's anything the BSDs need to do about blockchain unless it's, use Bitcoin to fund the next foundation. But I don't think that's going to happen. So the answer is mu. I don't understand the question. Other questions? Sorry, the mic's there. All right, time for a break.